Good afternoon, CTO. We are a business analytics team from Nanyang Technological University. I am Zhang Xinyu, and my teammates are Zexian, Sheng, Haozhong, and Yilin. Thanks for taking time to listen to our proposal of data management strategies for public transit system. We will deliver our proposal from 4 parts: introduction, business implementation, which includes our main design for the system, business outcomes, and limitation. Let me briefly introduce the background and problems first. As an essential component of the infrastructure, public transit plays a crucial role in promoting sustainable and accessible transportation for a community, reducing traffic congestion, boosting economies by expanding opportunities for dwellers, and addressing green gas issues. With advanced technology, different digital solutions can be deployed to better improve the public transit services, such as autonomous driving, electric vehicles, and artificial intelligence techniques. However, despite of their optimal features, effective data management is the basis for well implementation and business improvement, because high quality data enable digital plans realize to optimize operational process and improve services and achieve profits finally. A lot of data challenges are raised because of the rapid increase in transit demand and various sources of data in information systems. Large amounts of data from various sources, including passenger data, vehicle data, and operational data, first pose a challenge to data processing, integration, and analytics. Due to data share volume and different formats, data may not be processed and interpreted and provide insights for decision making. And large amount of data may lead to dark data issues if the organizations and employees fail to reuse this data to help decision making. The improper managed and stored data may result in performance issues, data duplication, and increased cost. What's more, sensitive information collected and stored in public transit services, such as passenger data and financial information, faces security problems. The data should be securely stored and protected against cyber attacks, theft, and unauthorized access. So, the main objective of this report is to establish a comprehensive approach to data management and analysis, including the implementation of data management system, data analytics tools, and security measures to achieve better public transit services and tackle these data issues. The techniques we include in the system design are centralized repository data warehouse, multi-dimensional analytics tool, online analytical processing, and big data processing technique Hadoop. Next, welcome my teammate Sheng to introduce the first part of our implementation, data collection and storage.
Thanks, Xinyu. Now I will continue to introduce the data collection and storage part in our group projection. So overall, we divided the data we need to use into 5 parts, including vehicle data and user data, order data, and data about train station and road condition. Firstly, about the vehicle data. In this case, for the convenience of description, we assume that all vehicle models are the same. Therefore, other information such as battery capacity, number of seats in the car, and charging requirements are completely identical. The vehicle's real-time speed, direction, coordinates, battery charge, mileage, and other data need to be updated to MongoDB in real time. Those existing attributes, such as the license plate and historical accident records, will be stored in MongoDB as documents. And next, since we need to arrange vehicles and routes according to user requirements, we need to obtain customer information from the mobile application. So each user's information includes a user ID, name, contact information, and a common address that can be stored in advance. For example, the geographic location of a home, office, or school can be stored in the form of latitude and longitude coordinates. But the user's real-time location needs to be written to MongoDB in latitude and longitude coordinates, along with the ID as the user's geographic location changes in other documents. The order data includes order ID, user ID, license plate number, starting location, departure time, ending location, arrival time, weather, order price, and rating. The data is stored in the database in a new document as the order is generated. And this document is updated in real time when the order is completed. The time spent on orders, weather, and so on will help subsequent analysis based on historical data to provide estimated prices and estimated time spent when customers request an order. This facilitates customers' scheduling. And for the train station part, in order to simplify the scenario, we make the following assumptions. So each train station has only trains with a predetermined route, and their starting point, passing stations, and ending points are the same. As the result, the train station data, including station ID, station name, and schedule table, will be stored in MongoDB. Finally, about the road conditions, we decide to use the combination of Google APIs. So Google Map will collect data from two aspects, including user data, which includes information about their movements, their history, and navigation, and also third-party providers, including Google Maps, also collects location data from third-party data providers such as GPS manufacturers, telecommunication companies, and mapping companies. So we are able to do the following. As for regulators and agencies, they can integrate with Google Maps through the Google Maps APIs. And for the companies based on distance, traffic conditions, road network, user preference, and other factors, Google Maps allows us to customize users' route based on personal preferences. Next, Zexian will introduce more about the technology we used.
Thanks, Chushu. Now I'm going to give you an overview of our data management pipeline. In this pipeline, we use HDFS and DBMS to store two different data sources, sensor data and well-structured data. The sensor data is stored in HDFS as log data, while well-structured data, such as vehicle, user, order, or train station, are stored in a NoSQL database. To make it easier for data analysts to process and analyze the data, we convert the sensor log data stored in HDFS into a more user-friendly format in Hive, which can be queried using circle-like syntax. This involves in defining the table schema, creating an external table linking to the HDFS data, mapping the data to the table, and loading data into a Hive table. After that, we use a staging or DBMS to carry out ETL operations to generate an operation data store. We extract both the converted sensor log data in Hive table and the well-structured data in NoSQL database and integrate them. Then we transform integrated data before they are loaded into the data warehouse, which is used to prepare a start schema for OLAPQ. The start schema includes a fact table and several dimension tables, linking via foreign keys. And aggregations are created to summarize the data in the fact table at different levels of dimension hierarchy. Finally, we build the OLAPQ according to the start schema prepared in the data warehouse. By parsing the build model, corresponding data is pulled from the underlying data warehouse. Though arranging and combining data by different dimensions, the aggregated values of these different dimension combinations are pre-calculated, which will establish the data queue. The pre-calculated values of the measures are stored in HBase, a column family database to handle large volumes of data and circle queries submitted by users. When requesting standard report, the predefined OLAP cube is used to accelerate the query, which allows us to analyze the logic and filtering the conditions quickly and efficiently. In addition, it is also possible for us to directly query sensor log data from the HAV table. In summary, this data pipeline allows us to process and analyze both large amounts of sensor data and well-structured data, such as vehicles, users, and so on. It enables us to make the data-driven decisions by improving our understanding of the vehicle's performance and enhance the customer experience. Then welcome Yilin to introduce the transit system.
Thanks, Zexian. Having a basic understanding of the framework of the marriage of the data and OLAP, this section will introduce 6 real-world applications of the system. First of all, we can provide instant updates of road conditions. As mentioned earlier, vehicles can sense the road conditions. For example, when the distance between vehicles is less than a certain distance, it indicates a traffic jam or traffic accident on that road. Therefore, the road condition can be updated. The road can be avoided to save time when planning the next trip for other customers. And the second function is the traffic incidence prediction. Since vehicles will share its traveling details like speed and direction with nearby vehicles, it enables computers to predict traffic incidents. Based on historical records, we can also send alerts when a vehicle approaches a high accident area in advance. Thirdly, the route planning function will give us personal recommendation. When the user enters a boarding location, destination, and other information in the mobile application and sends an order request, we can use his real-time coordinates to find a nearby vehicle. Here is an example. In the MongoDB, we can use geospatial query operator near. As shown in the figure, a total of 5 coordinate points was set up for testing, with a distance of no more than 1,000 meters. Selecting a certain coordinate as the pickup location, only 3 cars came out when the range is set to 500 meters, and 2 more cars will show up when the setting is 1,000 meters. This query provides technical support for us to provide users with recommendations for nearby vehicles. And at the same time, we will use Google API to find the best path between users' boarding point, train station, and destination coordinate. By querying the train station document, we can also find the nearest train that user can catch in the estimated time. And by loading historical documents and other data storage modules, we can provide user an expected price for reference. The fourth function is vehicle maintenance. In the vehicles document, we can look up information about the vehicle's battery usage, total mileage, and so on. So we can decide which are the best suited for the planned costs. When the battery charge reaches a certain number of times, we can arrange for the vehicle to be serviced to ensure passenger safety. And last but not least, it can provide customer service and it can improve customer service. We can query the historical information and find some business insights by calculating the average ratings of the order. For example, if there is an order with an extremely low score, we can query the details of the order and analyze what caused the bad review, such as a wrong route planning and unreasonable price, and then optimize the system to provide users with a better travel experience. And that's all of the brief summary of the business application part. Let's now welcome Haozhong to introduce more details of this system.
Thanks, Yilin. Next, I will first talk about the data management, security, and governance process for our proposal. In terms of data management process, we should focus on the management of dark data to save the storage in the company. Dark data problem happens when the data we store cannot be used in the future. Therefore, we should construct a framework of management. In terms of the data security, we should be able to find out the leakage of the data privacy of customers, both in the data collection, storage, access, and sharing process. As for the data governance process, companies should have a clear policy on the roles and responsibilities of different stakeholders, data decision-making processes, and dispute resolution mechanisms. From the perspective of our business outcome, we will analyze from the following macro and micro aspects: market size of the public transportation using Sheng and the impact of our design model implementation, respectively. First, the market size of the public transportation using Sheng is directly linked to our business perspective, since we designed the system to serve those who have the need to use Sheng as their transportation tool. According to the public data, the global public transportation market using Sheng was valued at approximately $142 billion in 2020 and expected to reach $184.9 billion by 2023, growing at a compounded annual growth rate (CAGR) of 5.4% during the forecast period. Meanwhile, the global market for autonomous driving car was valued at approximately $54.23 billion in 2020 and is expected to reach $556 billion by 2026, growing at a compound annual growth rate of 42% during the forecast period. The increased demand of the public using Sheng and the demand for auto-driving vehicles will build up a solid foundation for the development of our new technology in the future. Moreover, from the micro perspective, compared to traditional ride-hailing software that uses database management with tools to automatically schedule vehicles has several advantages. First, it can improve the accuracy by using AI and other big data handling tools. Second, it is able to enhance the efficiency of operation by automating the process of scheduling vehicles, vehicle condition management, real-time traffic data analysis, and optimal route scheduling system. Third, it can provide a better customer experience by analyzing the customer preference. Last but not least, it is capable of improving the data analysis process by collecting and analyzing large amounts of data from various sources. However, there are still limitations to our proposal in terms of the use of data management techniques. First, in terms of the data warehouse, it may exist a problem of data integration and quality. Second, in terms of the OLAP, it is weak in data volume and there are only limited data options. Third, in Hadoop, it may be over-complex and there exists a problem in data integration and bad performance. Overall, our designation is an innovation in the public transportation area where we can make use of data management process to facilitate our management and customer experience. Thank you for your listening.